So welcome to first lecture on the course called Ordinary Differential Equations. Today we are just going to introduce some basic notions. You are most likely familiar with all the concepts, but it really helps to provide a little bit of review as students sometimes get rusty. So what are we going to do? We will begin with some basic ideas. The course is called Ordinary Differential Equations. We refer to them as ODEs. So when you hear the word ODEs, it just means ordinary differential equations. Okay. What is a differential equation? Okay. A differential equation, or an ODE, is an equation that involves an unknown function and its derivative or derivatives. So for example, dy dx equals x is an ODE. It is an equation. It involves derivatives and it involves the function. You don't see the function here, but this is definitely an example. Another example would be dy dx equals y, or dy dx equals xy, let's say. Okay. The second thing is what does it mean? What does it mean to solve an ODE? It just means solve for the dependent variable. Okay. The next question is, what is an initial condition? What is an initial condition? So if I'm given a function like this, dy dx equals y, and I give you an initial condition of y of 0 equals 3, this is called an initial condition, because once you solve this differential equation, you most likely are going to end up with constants, and the initial condition allows you to solve for the ODE. The idea of general versus particular solution. Okay. So let's say I have dy dx equals x. This is an ODE. And let's say the initial condition y of 0 equals 3. This is called an initial condition. When you solve for y as a function of x, you're going to end up with something like this. Without the initial condition, the solution to this ODE is this. And we'll go through it quickly. But this initial condition will allow me to solve for the constant c. So let's go through it right away, actually. So dy dx equals x. We can solve this by separating the variables. So you have dy dx equals x dx. Integrate both sides of the expressions. You get y equals half x squared plus c. So this is called general solution. Now, once we utilize the initial condition, y of 0 equals 3, it means when x is 0, y is 3. So that allows me to solve for the letter C, which is 3. So now my function is half x squared plus 3. I believe it is 3. Yep. Okay, so this is called particular solution. Particular solution. Okay. Now, if you go back to the ODE I gave you, and if you combine it with the initial condition, and this is called the solution, so this is called the solution, happens to be particular because we use the initial condition. This is called an initial value problem. Okay? So quick review. So an ODE is just an equation that involves a function and its derivatives, like this one. Okay? What does it mean to solve one? It means you need to solve for the function y, in this case y of x. And the initial condition is this. You get, when you solve, you get a general solution. This is called general solution. Once you plug in the initial condition, you get a particular solution here. And this ODE with the initial condition is called an initial value problem. Okay? And this is my solution. So let me give you a few examples. So the one we did was this. dy dx equals x. dy dx equals, let's say, y. dy dx equals, I don't know, y over x. To be a little more practical, d squared x dt squared equals negative g. This simply says the acceleration of a mass is a constant. This is the gravitational force, 32 feet per second squared, or I believe it's 10 meters per second squared. And it goes in the opposite direction. Okay, that is a differential equation. One that you are very familiar with is this one. Okay, a population is proportional to the rate of change, or the rate of change of a population is proportional to the population. Another one you might be familiar with is Kp minus, let's say, Sp squared. This is a logistic differential equation. Here is another one. The spring mass system, or simple harmonic motion, mt squared x dt squared plus kx equals 0. That is another example. Or the one that represents the movements of a pendulum, L d theta dt squared plus g of sine theta equals 0. These are all examples of ordinary differential equations. So now we are going to categorize them. We're going to categorize them in 3 ways. Ordinary versus partial. And this is going to be very easy for us because we are not doing this in this course. Then you have first order versus second or third order. So we can categorize by order. We can categorize by whether or not they are ordinary or partial. And then, more importance, linear versus nonlinear. Nonlinear. So let me go through each one of them. This entire course is called ordinary differential equations. So we're only addressing ordinary differential equations. Partial differential equations might look something like this. So these are partial derivatives. If you remember from multivariable, we're not addressing these at all. So all the differential equations we are going to deal with are going to be ordinary. But it's important to know that there is a difference. First order and second order are also easy to address. First order means in your differential equation, only first derivative shows up. So this is an example. This is another example. And this is another example. This is another example. There is only a first order here. And this one as well. These are first order. A second order would be something like this one, right? Or something like this one. So this is second order. Put it in red. Okay? You could have third order, or fourth, or fifth, or nth order. But so long they're not first order, these are the first order, the ones in green, and the second order are the ones in red. And you solve them the same way. The way you solve first order is the same way you solve second order. You may have to integrate twice and get two constants and so on and so forth, but the process is the same. The hardest thing to do is to address the idea of linear versus nonlinear, this concept here. Okay? Let me erase this. It's bothering me. Okay. So, a linear differential equation is a differential equation where the dependent variable, let's say in this case y, this one, doesn't have, so look at dy dx equals x. The constants in front of the dy dx cannot be a y or a y squared or square root of y or sine of y, let's say. We call these linear. So this is linear. This is linear. Linear. This one is linear. This one is linear. This one is linear. So you don't see x or x squared here, okay? As the, let's call it the coefficients. However, this one is nonlinear, this one. Why? Because p squared shows up, okay? It's a logistic, nonlinear, ordinary differential equation, first order. So this is the first order, ordinary, obviously, nonlinear. This one is also nonlinear, this one. Now you don't see theta squared or square roots of theta, but you see sine theta. And the Taylor expansion of sine theta, remember, let me go here. Sine theta equals, I think it's theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus dot, okay? So this sine theta did not allow for L d theta dt squared plus g sine theta equals 0 to be linear. So this is nonlinear. Another way to explain it is to think of what we call a linear operator. Linear operator. A linear operator L of x, ax plus by is a L of x plus b L of y. A L of x plus b L of y. If a function satisfies this condition, we call L, or a F, you can use the letter F if you care, is a linear operator. You can split this into two pieces. You could say L of x plus y equals L of x plus L of y, and L AX equals A L of x. Together, make this. So for a function to be a linear operator, it means it needs to satisfy this equation. If you look at sine theta, the sine function is not a linear operator. Why? Because number one, sine of AX is not A sine X. And also, you don't need both conditions. One of them, if one of them is not satisfied, then it's not a linear operator. Also, sine of x plus y is not sine of x plus sine of y. In other words, sine of AX plus BY is not A sine x plus B sine y. So for that reason, the sine function is not a linear operator. And therefore, the function we mentioned here is a nonlinear ordinary differential equation, okay? So I don't know what happened, but I lost my voice there, but I'll just repeat what I said. So in conclusion, we haven't learned methods on how to solve differential equations, except briefly, we briefly made a reference to separation of variable on this silly differential equation. We talked about ordinary versus partial, linear versus nonlinear, which is important, and then the order of the partial of the ODE. One last thing I want to mention, which is extremely important. The nonlinear ODEs are either very hard to solve or impossible to solve. The majority of them are impossible to solve, but very few of them are solvable algebraically. And this one in particular that I shared earlier, it's called the logistic curve, is actually solvable. You may want to give it a try. As a hint, I would suggest you use partial fractions. This is the rate of growth, and this is the rate of decay due to death, and so on and so forth. You may want to give it a try to see if it works for you. But the key is, what we're going to do in this course is we're going to learn how to analyze qualitatively this type of differential equations without having to solve them. Even though this one is solvable, we could get everything that we want to get without having to solve it. Needless to say that many of them are not solvable anyway. So that should end this recording, and I will talk to you in the next session.